Now, in this video, I want to talk about the error signal and in the closed loop system, and we'll see how it behaves. For the closed loop control system that is shown on the slide here, we have already calculated the error as this, or we can calculate the error, right? Because uh, error is r minus y, and we have already calculated y in terms of r in the previous video, and we know that es is going to be this big value. Now let's just look at this error to see how we can reduce this error. Remember, the aim of a control system is to have the error zero. We want the output to follow the input. That's what we want, right? So how do we do that? Uh, to do that, let's just kind of simplify this equation and try to take a look as to what goes into getting that and getting to there. Now, if we open out these brackets and we subtract and we kind of do some arithmetic, just combine the first and the second terms, then we get this transfer function becomes of this form. Now, if we write ls as the loop gain, as the open loop gain, right, gc times g, ls is usually written for the loop gain and it will have the term h as well in it. But in this case, uh, we are just assuming hs to be 1. We assume that the gain of the sensor is 1. And that's why you can see that in this transfer function, hs is not appearing. So if you assume ls to be gc times g, then you can write this error in this form. Okay. Now, if we again write 1 plus ls as fs, which is the denominator in each of these terms, let's call it fs, and then define s as 1 over f. Okay. So if we write s as 1 over 1 over f, s will be 1 over 1 plus l, and c, let's just write c as l over 1 plus l. Now note that if you add s and c, you get 1, right? So if I increase s, c is going to reduce, and if I increase c, s is going to reduce. Okay. And now let's kind of substitute s and c into this equation. So take a look. What is the factor that multiplies rs going to be? It's going to be s, right? Because it's 1 over 1 plus l, which is exactly the term here. So you get s r, and then in here again you get s times g times td. So the disturbance is multiplied by a gain of s times g, and the noise is multiplied by c. Now what this tells us is, if I try to reduce the effect of noise on the error, what's going to happen? I reduce C. But if I reduce C, S is going to become high. So which means the effect of disturbance on the error is going to be higher. Now if I reduce S so that I can reduce the disturbance, then the effect of noise increases. So we cannot reduce the effects of noise and disturbance both at the same time in this system. Now, luckily, what happens is, in most cases, the disturbance and the noise are not at the same frequency, they are at different frequencies. So the noise is a high frequency signal, while the disturbance is usually a low frequency signal. And what this means is that you could choose S in such a way that it is very low at low frequency, and at that when S is very low at low frequencies, C will be very high at low frequencies. But then you can make sure that C becomes very low at high frequencies so that the noise also reduces. And at that time, at high frequencies, then S will be high, right? So we increase Ls at low frequencies to reduce S, and we reduce L at high frequencies to reduce C. So we can choose a controller which has uh, which results in a high loop gain at low frequencies and low loop gain at high frequencies. and that would kind of reduce the effects of the noise and the disturbance both together. And basically we can do that because noise and disturbance are at two different frequency bands.